So, welcome all to mathematical methods and techniques in signal processing. This is the start of the module for this course. In the previous modules, we just recapped the basics of discrete time models, basically reviewing what signals are, what systems are, and then leading to the state space representation, and we got a feel for what it is as the signal is going through a tap delay line, that it is a vector. And this formulation of the transformation of a signal to a vector is very important, because we can invoke the techniques in linear algebra towards a very precise mathematical formulation for our signal processing problems. So, this is a very important step. So, the moment we transform a signal to a vector, now it is in an abstract space, and all the mathematical techniques that we are used to in linear algebra we can now apply to the signals, and that is a very important step. So, let us recall some of our foundations in linear algebra. We will not be going extensively into linear algebra, but we will be touching upon the essential concepts which are required for this course. So, we will start with vector spaces. A finite dimensional vector may be written as some vector x having these coordinates x1, x2, so on till xn. So, we can say this is a column vector, and the elements of this vector are x1, x2, so on till xn, and each of the elements, they belong to some set such as maybe the real line, that is xi belongs to R, or perhaps xi can belong to a binary field. Now, they are the scalars of the vector space. Now, we will define what this linear vector space is. So, like we can imagine a finite dimensional vector comprising of some elements, and these elements can belong to some real field or some other finite field, and there also we have scalars for this vector space. So, with this we are in a position to start with the definition of a vector space. A linear vector space S over a set of scalars R is a collection of objects known as vectors together with an additive operation and scalar multiplication satisfying the following properties. So, this is a linear vector space S over a set of scalars R is a collection of objects known as vectors together with an additive operation and a and a scalar multiplicative operation satisfying the following properties. So, let us see what the properties are. S forms a group under addition. Now, what are the properties for a group? We have closure, we have associativity, then we have identity, existence of the identity element, and then existence of the inverse, right, these 4 properties. So, we will just enumerate and list all this. So, for any x and y belonging to S, x plus y belongs to S. Take an x, that is a vector x belonging to S, take another vector y belonging to S, x plus y should belong to S, right, this is closure. B, there is an identity element in S denoted by this null vector such that x plus 0 is 0 plus x, which is x. This is basically the identity element, 0 is basically the identity element for this. Then for every element x belonging to S, there is another element y belonging to S such that x plus y is equal to 0. Pull a vector x belonging to S, there exists some y belonging to S such that x plus y is 0, and y, which is basically minus x, is the additive inverse. Addition operation is associative. This means for any x, y, z belonging to S, x plus y plus z it does not depend on the grouping. You can group x and y first, add them up, then add z, you can group y and z and then add x, and that result is the same. So, this is one set of properties. S forms a group under addition. For any a and b belonging to R, that they are scalars, and x comma y belonging to this set S, Ax belongs to S. Pull a scalar, multiply this with this vector that belongs to this space. Now A times Bx is basically AB times X, and then if you take A plus B times X, which is basically X plus Bx, this is basically it is distribution, and then you take A times X plus Y, this also distributes, it is Ax plus Ay. The other property is there is a multiplicative element, or I would say multiplicative identity element precisely, which is 1 belonging to R, such that 1 times X is X. So you multiply the vector by the identity element, you get back your original vector, and there exists 0 belonging to R such that 0 with X is basically your null vector. Now these are basically the properties of a vector space. So if I give you a collection of vectors and possibly some scalars on some set, and then if I ask you if this is indeed forms a vector space, you have to verify all these properties are true. Okay. Then we will see some examples of vector space. A most familiar vector space is basically Rn, that is a set of all n tuples where each of the elements are basically reals, right. This is a very familiar vector space. So if say n equals 3, you can think about x1 is say some 1 2 3, this is belonging to R3. Similarly you have 0 1 8, this belongs to R3, so on. And there are other examples, slightly non-trivial, but it is conceptually very easy to imagine. Set of m by n matrices with real entries. Can you think about this as a vector space? Set of all m by n matrices with real entries. Then is a set of all polynomials this is very important, up to degree n with real coefficients. So set of all polynomials up to degree n with real coefficients, this also forms a vector space, right. So imagine a parabola, right, the degree is 2, maximum degree is 2. That means I can have ax square plus bx plus c, right. A, B, C are all reals, right. So now can you think they form a vector space? Take one parabola, add another to it. Take one polynomial, that is second degree polynomial, add another polynomial to this of up to that degree. Verify if you are going to have the space of all it belongs to the space of all polynomial up to degree 2. That gives you sort of an idea. Scale up parabola, you can stretch it, right, or it, since it is up to degree n, a line is part of that, bx plus c is part of it, a constant c is part of it as well. So it covers the entire space. So therefore this is indeed a vector space, but I will leave this as an exercise to you to sort of formally verify if all the axioms are satisfied. Now this idea can be sort of thought about in infinite dimensional vector spaces. So these examples include sequence spaces wherein we have a set of all infinitely long sequences xn. The other possibility is the set of continuous functions defined over the interval a comma b. So these are all infinite dimensional spaces. A good example when you have to think about expanding these continuous functions is the Fourier representation, right. If you think about a signal and its Fourier representation, and each coordinate of the signal representation is basically a point in this space, in the signal space, and that is basically an infinite dimensional vector space. So we will get into that. I think that is where we are leading towards. So we have another notion of a subspace. Once we have defined a vector space, we have something called a subspace. Let S be a vector space if V is part of this space is a subset such that V itself is a vector space. Then V is called a subspace of S, and we will see this through some examples. So we will take the example of codes, binary codes. Let S be equal to this set and the addition operation is basically modulo 2. Can we think of this as a vector space first, right? You take 0 and add it with any of these 3 elements, you get back the element, right? If you take 0 1 0 0 1, you add it with this, you will get this back. So this is basically like an identity, right? So think about what 2 elements you can add to get this 0, right? For example, if I were to add 1 1 0 0 0 with say 1 0 0 0 1, right? Suppose I added these 2 elements. So basically this you will get this element. So closure is verified. Now it is, if you add the same thing, same vector with itself under modulo 2, you get the null vector, right? 0 1 0 0 1 plus 0 1 0 0 1. Under modulo 2 it is basically 0, it is trivial, right? So you can think about it as a self inverse. So it satisfies all the properties, and over this binary field basically you can only think about zeros and ones as your scalars. So 0 times anything you are going to get back the 0 vector, 1 times this vector you are going to get back the same vector itself, and you can verify the distributive properties, etc. So this indeed forms a vector space, right? Now suppose I choose this set V to be 0 0 0 0 0 and 0 1 0 0 1. Can you verify is V a subspace of S? That means V should be contained in S, the elements are definitely contained in S, and just quickly check through the axioms that we did earlier, that it has to be a group under addition and the distributive property and the multiplicative identity 1, right. So 1 times that vector is basically x, you get back the vector, 0 times the vector is you have the 0 vector here, distributive property is carried out, and it is a group under addition, right. So this is trivially verified. So it is indeed a subspace of S. Now signals, this is very important for us because it is a signal processing course, not a linear algebra course. So we have to bridge the connection. Signals can be thought of vectors in a signal space. And the notion of vector space can be naturally extended to signals. So this is a very important point that we should always be thinking through, and this is what we are going to get towards the end of the first module basically, which is review of vector spaces, inner product spaces, signal spaces, eventually towards signal geometry. This is where we are getting towards. So clear so far with the basic definitions of vector space and subspace.